to all. This is Vaishnavi, Assistant Professor, IT Department from SNS College of Engineering. Now we are going to see about the process synchronization in operating systems. Process synchronization. Processes can execute concurrently, may be interrupt at any time, partially completing the executions. Concurrent access to share the data may result in the data inconsistency. Maintaining the data consistency requires the mechanisms to ensure the orderly executions of cooperating process. Illustrations of the problem. Suppose that we want to provide a solution to the consumer or producer problem that fills all the buffers. There we have that producer and consumer while true condition followed by this while counter is equal to buffer size, and then buffer in is equal to next produce, then in is equal to n plus 1% of buffer size. Here counter plus that is incremental happens for that consumer while true condition. Next, while counter is equal to 0, then next consumed is equal to buffer out is equal to out plus 1%, buffer size counter minus here decremental. Next one, critical section problem. Consider the system of n processes, that is P0 to P1 up to Pn minus 1. Each process has critical section segment of code. Process may be changing the common variables, updating the table, writing file, etc. When one process is critical section, no other may be in its critical sections. Critical section problem is to design the protocol to solve this problem. Each process must ask the permission to enter the critical section, may follow the critical section with the exit section and then remain sections. Here we have the gender structure of the process PI, that is due entry section, followed that critical section, then exit section, followed by this we have reminder section, and then while true. Solution to the critical section problem. First one is mutual exclusions. If process Pi is executing in its critical section, then no other processes can be executing in their critical sections. Progress. If no process is executing in its critical section and there exists some processes that wish to enter their critical section, then the selection of the processes that will enter the critical section next cannot be postponed indefinitely. Third one, bounded waiting. A bound must exist on the number of times that other processes are allowed to enter their critical section after the process has made a request to enter its critical section and before that request is granted. Next, we have the two approaches depending on if kernel is primitive or non-primitive. Primitive allow the perception of the process when running in kernel mode. Next one, non-primitive runs until exits the kernel mode, blocks or voluntarily yields the CPU. Synchronization hardware. Many systems provide the hardware support for implementing the critical section code. First one, allow all solutions below based on the idea of locking, that is protecting the critical regions via the locks. Next one, uniprocesses could disable the interrupts, that is currently running code would execute without presumption. Generally too inefficient on multiprocess systems. Operating systems using this not broadly scalable. Modern machines provide the special atomic hardware instructions. Atomic is equal to non-interruptible. Either the test memory word and the set value or swap the content of the two memory words. Here we have the solution to critical section problems using the locks, that is do acquire lock, then followed by this critical section and then release the lock, then reminder section and while condition is true. Last one is mutex locks. That previous solutions are complicated and generally inaccessible to application programmers. That is, OS designers build the software tools to solve the critical section problem. Simplest is the mutex lock. Product a critical section by acquire a lock, then release the lock. Then Boolean variable indicating if lock is available or not. Thank you.